Hello, everyone. Can you hear me online?
Yes.
Okay, so welcome to this session. This is our last session for today, and we will discuss about synergies between Rubin and Euclid. So I will be chairing this session. I'm Vincenzo Petrecca from Mina of Napoli, and Lian Guy will be chairing the session with me. So first of all, I remind you, we have, I cannot change the slide. We have a code of conduct, so be aware of the code of conduct and also the sticker that people can have on their badge. And also, this is a hybrid meeting, so we have people connected online. And remember that if you want to ask a question, people online can hear you only if you speak to the microphone. So please raise your hand and wait for the microphone before speaking. And also introduce yourself before speaking so people online know what you're talking about. As I was saying before, this session is about synergies between Rubin and Euclid. As you know, there were a plan for a set of derived data products. So this is the agenda for the session. We will listen from Jean-Jacques Couillard, who is online, about Euclid and the Q1 dataset. And then Todd Lauer will talk about the DDP implementation working group plans. And then we will have a series of talk discussing various topics. And in the end, we plan to have an open discussion. So I will leave the floor to our first speaker, Jean-Charles, who is online. You are free to share your slides.
Okay, so I believe you're seeing my screen now.
Yeah, we see your screen.
Perfect. So I'll get going. So thank you for this opportunity to contribute again on the topic of DDP. It's been quite a while. And I thought, like, before we talk about the Q1 and what it brings as synergies and elements for the future for work together, it'd be a good idea to take a step back and look at what happened over the past few years in terms of how far we've come from publishing this report 3 years ago almost. So here, just like, again, maybe some people in the room just don't know all the whole story. So this is some elements about why the DDPs are what they are today. And so we here with two really big missions and motivated by the study of dark energy, which is our core science. And we're building complementary imaging data sets. We have multiband, very deep optical multiband and versus high resolution plus near infrared coming from for ground and space. And so the two projects have been really talking to each other because of these very synergies we're talking about today. And but as a matter of fact, from the get-go, we knew it would be complex because the data policies from both projects do not allow for pixel sharing. So we had to find a solution. And so the path forward happened some years ago where the idea, the fundamentals of the DDPs is let's maximize the scientific return of both projects in a way that protects the science that is unique to each collaboration. So that's really the core element of the starting point for the DDPs. And then the idea was like, let's put this data set together, let's make some products, and then we'll be sharing them openly across the two collaborations, so very open. And but because we want to ease the process, and because there's lots of work that has gone into mastering the data set for each respective projects, of course, we knew there would be elements of the algorithm from the main pipelines of both Rubins and Euclid involved into the production of those DDPs. That's kind of the idea. So back in December 2021, we published this report, and we got me and my colleague Leanne. We got a lot of help from a large community of people who really, penned like important sections on various aspects of all the science that we could cover through these DDPs, and it really covers the whole range of Redshift, which is really wonderful. And out of that, so we had like about 60 plus DDPs. Some were not compatible with what the definition of a DDPs could be, so they were dismissed. But in the end, we still ended up with a lot of them. And once we took a close look at this, clearly there were some which were really helping generic science in a broad way. And so we call them cross-cutting DDPs. And the other ones where if you produce them, you will be enabling the core science and a vast range of complementary science goals. And then there were more specific DDPs, and those were more like focused on specific elements and science motivation. And we treated them all equally, right? So they were all pushed forward as being, okay, hold on, last you a second here, as they were really all pushed forward to being implemented. It's not because it's of course, the cross-cutting DDPs, as we're going to hear it from Todd, are going to be getting a priority, but we're seeing activities already today at different levels of the science collaboration or science working group in various projects, really thinking and how to develop those DDPs. And so this is really wonderful to see. And so we also see like it's a lot of DDPs, right? 60 plus. And so we knew they couldn't all happen at once or right from the beginning. And we know there would be some delays, and we didn't know exactly what would be going on. We were just coming out of COVID, and eventually, we managed to launch Euclid, and now you got your first light for Rubin, which is wonderful. So but we kind of had to scope what would happen in terms of calendar, and so we set a tiered approach, or like this is the most important one. This one should come first. So we had a roadmap and say, like, this is important, this is less important, and it was kind of a roadmap that would be handed out to the implementation group, and we'll be hearing of this following my presentation here. So quick reminder, I won't go into detail, just focusing on the main topic of what these main DDPs are. So we first thought like, well, since the timing might be short, and so we'll have to have some kind of a quick DDP, and that was the DDP1, which is a list-driven photometry catalog. And so as you hear it, it's kind of something that might not happen because of the calendar and the priorities have evolved. So it might be going straight to the DDP2, which is you need to have pixels at the same location at some point. And so some infrastructure has to be put in place so you can make this force photometry catalog happening. And then the DDP3 would be more advanced, and you will have deblending and all the fanciest elements you can do once you have more time also, because we are some element of tension in the calendar upcoming our way. Then ultimately, sometime we hope to have this DDP4, which was a wish that in the end, when you look at people want photometry, but photos is really a big pillar of all the science we need to conduct, we want to conduct. And so there was this idea of possibly doing pixel photometry redshifts at some point with all the deep learning method there. So we'll see. And then, of course, there were many requests for cutouts because of compact sources science. And so this was promoted to a cross-cutting one as a DDP. So this one is high priority. So at the time of the report, it was not just about what we want to do in the future once the data set are in hand. It was really about also, let's ensure that to have the best products, you need to have both telescopes look in the same location over the sky. So let's make sure first we have plans that are compatible with each other. And so when we look at the wide survey and the deep surveys, there were certainly some actions that were worth in considering. So at the time, Euclid was still defining a survey, and so was Rubin, and we knew that we had to, there was some ways of approaching the program from both sides, and so everyone slightly tweaked its plan so that the DDPs coming out of this effort would be maximizing sky coverage. And then there was the idea of like, okay, on the deep fields, we would have two fields, and one would be the Fornax, which correspond to Chandra deep field, and the other one was opening a whole brand new field further south. I'm going to show it in some maps when we talk about Q1, and that became the Euclid deep field south. And so that Euclid deep field south is a very peculiar situation with respect to the whole spectra of products you can get with the DDPs, in the sense that while the DDPs, the main DDPs, will be produced based on the data set that no one can see in terms of pixels, the EDF South was agreed through the MOU between Rubin and the Euclid consortium to actually be open from raw data, any intermediate products, and so on and so forth. And the idea behind that was like, well, let's make sure that everyone has access to pixels so we can play with it and essentially enhance possible DDPs and get the whole thing. So that's something that is about to happen as you start the observation with Rubin. And we already have a few visits of EDF South with Euclid. And so the idea is just these pixels will be shared really openly across the collaboration. It's not just the people doing the DDPs, is what I mean. So it's a nice cosmological field. So here we are in terms of once where was that, late 22, when the SCOC decided like this is going to be some definition on the actual outline of the LSST. We knew that in the South Galactic Cap, it would be trimmed at about +2 declination and +15 plus the Virgo burp there on the top right. And so immediately we adapted the Euclid plan and we trimmed everything we had in terms of plan coverage in the South Galactic Cap above +2, which is what I'm pointing here. And so that was the thing. And so we maximized, we're already from the start, making sure that because the launch of Euclid wasn't far away, we had to settle on the plan very quickly. And so we trimmed everything that was outside the LSST plan. And then that meant that on the north, we had to find some other solution at the Union survey, but that's not the topic today. And so here you see in green the maximization of what the LSST survey would be in green. And in yellow, you have the outline of the Euclid region of interest, which is where we'll be observing. And so then in some parts, so Euclid made an effort, trimmed some elements, and then there were some elements where also Rubin pushed the LSST a bit further south, and that was the Euclid extension that was in the SCOG report from last year, and about an additional 200 square degrees. But by doing so, by having this slight evolution of the LSST, that really ensured that anything that is observed at full depth by the white phase deep is covered by Euclid and vice versa. So we have a complete coverage of wherever Euclid looks in the southern skies will be covered by LSST. And then there was also discussions on the dithering, the optimal dithering for the EDF South. Again, those pixels that will be fully open to both coloration. And this one, because of the cadence you've adopted by the LSST, you get the idea here how many years it will take to match actually what Euclid will be doing. Knowing Euclid started about a year and a half ago, but Rubin will be catching very quickly. You can see it's because it takes only a couple of years to reach the full depth of Euclid. So eventually, as you keep going, the depth will be even greater than what is actually required from the get-go in terms of matching the Euclid depth for photo-Z. So this is all happening. It's wonderful. So here, just for the slides, I presume you'll be sharing the slides, but I give a global update of what the depths are in relation to the whole elements we're putting in place here. So you have the depths of the wide survey, what the DES has achieved, and that we're using currently for our DR1 effort on the Euclid side. Unions is a ground-based coverage of the northern sky, the static LSST of the north, if you will. And then you have this year one that we expect to use in DR2. Those are the depths. And in key importance is the coverage. So you can see the southern sky will be equally covered from north and south. And then you can see as we grow up in area, eventually it is indeed, as we expected, the LSST that will be covering most of the Euclid sky at the end. So this was just a quick conclusion. Like I said, there's no lesser partner in this effort where we want to maximize the science return for everyone. And we wanted really, again, covering just the core elements, but the DDPs, we really want them to happen for everyone who was involved in making so. So now with that said, let's jump to I was asked to give a quick update on the quick data release one that we released in March, a few months ago. I think the idea behind is like Q1 is public, you have DP1, what can we do with it? So what is Q1? Q1 is a single pass of the wide survey over the deep survey. So it's a sample, kind of a taster of what the wide survey will be. We picked the deep field surveys because it had the double goal of also introducing these fields. But essentially give you a taste of what the wide survey by Euclid will be. And so meaning it is what the main DDPs will be about. Here, this is like the programming of a telescope. And I'm just doing this pie chart here where you can see the EDF, the deep surveys in the end will be using about 11% of the time. And the wide survey is using about 66%. So 2/3 of the wide, 10% of the deep field. The rest is calibration and so on and so forth. While Q1 is single pass, I think the people are certainly interested in what we're talking about for the future, that in terms of number of paths will be over the field, we'll have about 40 of them. And so it means that the deep survey, after 6 years of survey of Euclid, will be about 2 magnitude deeper than the wide survey. In terms of visits, nothing has changed much since we put together the information in the DDP report, and we'll see stuff incrementing over time. But it's happening now, and so once we get the flow going in terms of pixels for EDF South, which is Q1 is going to give us a great sample, more on this in a second, we're going to get the data flowing. So this is close to what is happening now, and from L2 on Euclid. In green is year 1, in blue and red is year 2, blue is year 3. You have the legend at the bottom here. So you get to see we see a balance between north and south, and as it happens over time, we flip and always trying to sample the best sky, which is a darker sky you can get from L2. Again, quick reminder of the depths. We've covered this before. And here, in terms of information that is openly public, that's everything I'm providing here is accessible on the Cosmos pages from ESA. And you can go there. I provided the links, and in there we provide documents that explain exactly what the Q1 data release is made of and where we're looking at, and so on and so forth. So the next slides are about that. I wasn't so sure that what I could share, so I made sure that I went to the public pages as I made these slides, so I don't get yelled at. There we go. So the Q1 fields definition. So Q1, like I said, is a single pass over each of the deep fields. And the one of interest with respect to DP1, I believe, is EDF South and Fornax, which were both visited. So you have the link here. In terms of products, so of course, it goes through a whole range of all the elements that are produced by the Euclid Consortium ground segment. So you have calibrated frames, your spectroscopy, and so on and so forth. And we have no time now to cover this element, but essentially all the advanced products are offered and available on the archive at ESA. And so for describing all this, And again, it would take a whole session to go through all the elements, but the Euclid Consortium Science Grant segment did produce a suite of papers, 1, 2, 3, 4, 5, 7 of them, that give you all the details of what you need to know if you use those products. But you also start with LE1, which has a raw data. So there's all sorts of ways to deal with a Q1 data set. So here, in terms of now jumping to DP1 and ComCam, when we had the discussion about ComCam visiting EDF South, we talked with the management, say, hey, why don't we pick an area of special interest in EDF South? So here you see EDF South as a whole, as part of, that's a Q1 map. And so here, I believe DP1 is a bit broader than the actual square that was a single ComCam pointing here. But at least we propose to have it centered on this ROS. It's kind of the name of a pointing on Euclid, number 06596. And in there, I kind of looked at what could be something that would serve everyone. And so I look around the whole EDF South and say, great, we have a galaxy, which is essentially resolved by Euclid. We have a bright star, looking at effects, optical ghosts, whatever. We have clusters of galaxies of various size. So there seemed to be something that would make everyone happy. So we went for it. And so I'm very happy to hear more about DP1 at some point, because this is what is happening now. And if you want to have a full view of Q1, it was fully processed and fed into ESA Sky. So ESA Sky is a fancy navigator for images of the sky. And we made a color render of the whole Q1 at the Viz resolution. And in particular, that area that I just mentioned is fully available there. And I'll stop here. Thank you for your attention.
Okay, thank you for the talk. Any questions? Yes, there is one.
Hi, Jean-Charles. Robert Lupton. I couldn't quite understand from what you were saying, who is going to have access to the full pixel data? I mean, I as you know, I stopped working on this a long time ago. But are you intending to hand over the data that is being released by Euclid and Rubin to each other, to everybody in the collaboration, so other people other than the anointed team can work on optimizing the data sets? Are you putting out just a small subset of the sort that you're talking about in the Euclid Deep Field South overlapping with DP1? So really, how open is this project for maximizing the science across the two projects?
Hi, Robert. So the EDF South is meant as the data set, which is 23 square degrees again, and with many visits, that will be open to all in many ways in terms of products going from raw data to advanced data. And so whoever wants to be more involved in terms of understanding and optimizing new DDPs or fine-tuning will be welcome to it. But in the major effort for the DDPs will go through a subset of teams which have privileged access to the data sets.
Okay, so 23 degrees is significant. Thank you.
Yes.
Other questions? Also questions online?
There is one. There is a question from Dan. It says, was the discussion of sharing the ECDFS Fornax data with the same terms as EDFS? I'm not aware of that, but Todd and the implementation working group might have discussed that. I don't know. No, okay, Todd says no, he hasn't discussed that either.
Well, Fornax is not part of the MOU, so we can't show.
No, I think the question was, has there been any similar talk about doing that as well, i.e., I guess, adding it to the MOU or having a new MOU? But it's not part of the existing one, no.
Indeed. Yeah. The reason is just a few extra seconds is only Rubin can make the observation of EDF South. And it was the only telescope in the world in a position to cover that field. And when ESA and the Euclid Consortium approached Rubin, because it was a significant effort on the Rubin side, we said, hey, you know, let's go beyond the Call of Duty in terms of making a deal here and be more open about what could be happening with the data set. And so out came the idea of like, hey, let's make it really fully open to both collaboration.
Okay, if there are no other questions, let's thank the speaker again. Thank you for the talk and also to be up so late in Europe.
Sure, thank you.
Screen. Okay, so our next speaker is Todd Lauer, and he will talk about the data implementation working group.
Thank you. I'd like to thank John Charles for a wonderful introduction. Some of this will be redundant, but I'll go into a little more detail about what we're doing. So I am one of the two co-chairs of the Rubin Euclid Derived Data Product Implementation Working Group. The other is James Colbert, who represents the Euclid slide, who is not here today, and there is our membership. So I think it's obvious to anybody who thinks about this, and from the last talk, that putting to get Euclid and the Rubin observations together is excellent for any number of reasons. And they're complementary. The Rubin has depth, Euclid has resolution, infrared coverage, and so on and so forth. The tricky part, though, is that both projects were approved and motivated by the fact that they could do the science with their own observations. And so these are not budgeted or programmed in to combine the data. So the tricky thing that we have is to find resources and a path to producing joint data products between the two projects. So also mentioned by John Charles is the wonderful paper that Leanne Guy led the effort for, which defines the derived data products. I strongly recommend that all of you who are interested in this problem have a look at that document. There are a few things in there I want to mention. One is it began with a bottom-up effort. It organized scientific questions into Aries, transits, solar system, active galactic nuclei, strong lensing, so on and so forth. And each group produced what they wanted to put together between Euclid and Rubin. From their desirements, they produced a large list and then integrated over that and came up with common needs for all the groups. And these are the cross-cutting data products and derived data products, and there are 5 of them. And this is what we have focused on. And that's really what I'll be spending most of my time talking on. So our priority is to do the big pieces first, and then to move down and do the specific things which are left behind and not covered by the cross-cutting products. So there are 3 DDPs at the top, and I liken this, if you excuse me, to if you're flying standby, coach, and first class. And so the first DDP1 is one step above a simple combination of catalogs. Euclid has a catalog, Rubin has a catalog. You can match them and put them together. That's not DDP1. But if you take the catalog from each one and you go to where your object from your side of the street is, you can do forced photometry, okay, and get an answer for your source. So you're in Rubin, you have a Rubin detection, you ask of Euclid, gee, what do I have in an aperture around there? You know, just integrate up the flux, that's DDP1. A more sensible thing is, given a detection from Rubin, is to go to Euclid and say, let's now, in this particular area, rework all the detection in that area and come up with some photometry for my object. And of course, this elides the fact that Rubin has different resolution than Euclid. DDP3 is the most sophisticated approach, is say, we're just simply going to ignore the catalogs from both surveys, put these together, okay, and completely redo the source detection, deblending, and everything else ab initio with the resolution from Euclid, the depth from Rubin, the wavelength coverage, and produce a master catalog. And that is something which is down the road. But the first things that we're going to try is probably DDP2. So just to give you a little bit, there's a bunch of codes there. These are elaborated in the Guy et al. Paper. T is a time priority in years. P is the initial priority. U is a little different. It's the urgency. And then that code is tied to yearly release or major data release, where these things will come from. The little b there is this will be beneficial to both, as opposed to something which is of interest only to Rubin or Euclid. But the short story is, and this goes back to my silly standby coach in first class, is this is increasing complexity and sophistication as you go through these. This is probably most of which I just said. We've had quite a bit of discussion on how we want to proceed with these, and the feeling, it's not a complete consensus, but it is a strong consensus, is that simply skipping forced photometry may be expedient and going directly to developing a DDP2, where you rework the detection given a detection in one of the other sources. I should also say, because Robert asked about this, and I'm not sure I want to go into this in great detail, the Guy et al. Document detailed in very painstaking detail the data rights between Rubin, Euclid, and who has what, who's allowed to do what. Most of the conversation that we're having today, and which we're now exploring from, is from the publicly released Q1 survey from Euclid and DP1 from Rubin, which I think elides over these particular issues. But for any particular application, we are very much aware of the data rights issues, and that is something that we are trying to keep up front when we talk to the projects, and something, because there are a lot of people that have put a lot of work into this, and we want to make sure we respect the wishes of both projects when we talk about this. So what can I say here? Yeah, this just outlines what I just said. DDP3, as I said, is the most elaborate one, and we are not quite engaging in this. This is, simply combining the images directly from both surveys and beginning the actual source detection and generation of catalogs. Here's a bit of what we've done. We are convened in 2023. This is a little bit more in the data rights. Some of the restrictions are to ask a question of Euclid. You have a 5 sigma detection in your catalog. If you're Rubin, then you go to Euclid to see what's there. That is, you're not looking for faint sources from Rubin to see if there might be some similar faint source with Euclid. These are solid detections in Rubin. This is part of the data rights discussion. Okay, let me just continue. Go ahead. I don't know if I can answer it, but.
Go back to that slide.
Yeah.
I'm sure you can answer it. I just wanted to, it went by quickly. So when you described the first thing, the different levels, DP, standby economy and first class,
Yes.
I thought I understood that with the forced photometry. But what you're saying on this additional roadmap information is that both sides of that won't be shared with both collaborations. So in other words, Rubin will get forced photometry on Euclid, and Euclid will get forced photometry on the Rubin data.
It's a little different. I'm not sure. Let me see if I can answer the question my way and make it my own question. So you have, say you're Rubin, okay, you have a source catalog, and your sources must be, to be able to knock on the door of Euclid, you have to have a threshold, and it's a 5 sigma detection, okay? So we're not gonna let you go to Euclid if you've got a little, you know, smudgy kind of thing that you're not sure about, okay? Given that, okay, you can then go and say, we will reprocess that area and see what is in Euclid at that area, okay, to match up.
Right, I understood that. I
Did
guess
you
the
want
part-
to add something, Lee? Okay.
Yeah, I understood that. I guess the question was, that's all in Rubin we get to see. We don't get to see it from the other side, and vice versa from Euclid?
I can't answer that precisely. I do not know how that product, or it is using, in fact, actually, I would say, if I understand it rightly, they can see the other side. Okay, but there's a complementary thing. The people, the Euclid side does the same thing.
Right.
Okay, we've got this 5 sigma thing here, but they won't have the depth. And so they can go say, you know, say what colors do we have, you know, from LSST to augment our stuff.
I guess I'm asking a much more basic question, which is that in this area that we've decided where we're going to have joint products, will we both see the catalogs and force photometry, say in Rubin, when we see it
I
from Rubin and
believe that
Euclid?
is true, but I want to be careful about that because I'm not a lawyer.
So we have been discussing that on the Euclid side, and what we were told is that from the Euclid side, we will do force photometry on the Rubin images using the catalog from Euclid. And on the Rubin side, the contrary, you will use
Yeah.
the. My question is, now, there are some of us who are in both collaborations. So the Euclid members will have the Euclid catalog, the Rubin members will have the Rubin catalog. And those that are both in Euclid and Rubin will have both catalogs. So are there MOUs or agreements for people that are in both collaborations to use which catalog in which publications? Can we use both catalogs?
Yeah, and I don't want to answer that because this would be my own ignorance to produce an answer. What I would say is, look at the Guide-all document for each of the DDPs, and there are the discussions of how we would proceed for the Rubin side versus the Euclid side. And if that is unsatisfactory, or if there are concerns, this is the sort of thing we'd like to hear about before implementing. I can say that the one thing we don't want to do, and this I would make a strong statement, is we realize a lot of thought has gone into this, and there is a lot of concern. And so we want to make sure that whatever is done is satisfactory with both products. We're not going to surprise people, you know, with some arbitrary decision. This is clearly something that's very important, and we hope that we will be handling this correctly. That's the best I could offer today, standing in front of you.
Be a document by the implementation team that will specify what the agreement.
It won't be a documentation by us. I think we will collect the questions and issues, and we will ask both Euclid and Rubin, okay, what do you want to do about this, and come to a mutual agreement where both sides are happy. Again, we want to be very careful about this. We ourselves have no authority, okay, and that's important to understand. It is our role to manage this and to ask the questions and to poke the projects, but we're not going to make rulings ourselves and say, no, you know, this is how it's going to be. Okay. Let's see if
Yeah.
John Charles.
Yeah, just a quick answer. I don't want to take too long, but we wanted to make sure there's no different class of citizens when it comes to DDPs, and everybody has to be treated equally. So from the get-go, we knew there would be that question like, oh, I'm in both collaborations, so do I get extra privilege? The answer is no. It's like the people who have access to both, you know, projects cannot create something because the paper will actually be stopped at the time of the publication by the respective editorial boards. And so that kind of dictated how we would develop the DDPs and the access and so on and so forth, so that it's really equal, and we try to bring the greatest fairness across.
Shall I go on?
Please.
Please.
Okay. So one of the things we have tried to do is just gather information as to who has what capability and who is interested in doing work on this problem. Again, we are not a source of work. It does not fall to our group, to actually do the work, the image processing necessary to make this happen. It is our job to find resources and the path to making this happen. It is quite clear from a community workshop that we had, that there is an immense, and this would be known to all of you here, that in answering these questions from a technical point of view, how do you blend the two instruments, is, a leading edge research problem with many different solutions and many different kinds of thinking about how to do it. And again, it's not our job to say, oh, we think this one is the best and let's go with this. What we see happening is we'd like to enable people to do this question and to produce DDPs. And we will, if we can make them available, again, with all the appropriate protocols, it will be those who use these for research, who evaluate them and so on and so forth to sort these out. And this, of course, is quite common in the field. I've been around a while, and you can find, 20 different ways of doing photometry, and you decide what makes most sense for your problem and so on and so forth. So I think this is the last slide I have here. Yes, so what are we doing now is that we've had a workshop to gather information. We have made some subgroups. We have a simulation group to see what simulations can be used to provide for exploring algorithms. We need computing resources. That's another group to look at that. I think one of the things, though, that is most interesting is we have, I think, started up or encouraged the start up of some demonstrations of actual productions of some of the cross-cutting DDPs, particularly DDP2. I think DDP1 is not being touched. And so we have sort of, I don't know if to say 3 or 2 efforts. We have one collaboration, which is 2 teams, one led by Simona, and I misspelled your name there. I'm sorry. I got an extra, yeah, I know. I got an extra R in my name, so this all balances out somehow. So Simona May at the APC and Joe Moore are working together to produce DDP2 from the Q1 and DP1 releases. And then also who are here is present is an independent effort by Gautam Narayan working with NCSA and possibly the Danish Independent Data Analysis Center for Compute Resources. And so these are separate groups that actually try out the work. And in doing so, we will explore the problems of, how do we validate them? How do we make them available? How do we respect the data rights? So on and so forth. And already has come up, these are people interested in actually doing this for science, surprise, surprise. And so there's also a question of how do we have joint publications between the 2 groups, again, that respect all the people from both sides who have put into the efforts. But I think this is how it's going to go. We are going to encourage people to try this. We're going to see what happens and, try to do this within the framework given to us by Leanne's document. And one last little thing I'd mention here, we have begun talking to the, I don't know if I said, is it the LSST science collaborations or the Rubin science collaborations? I think it's LSST because it's a survey, the science collaborations. So to pick up some of the other DDPs that aren't covered to make sure that we're covering the full spread in the document. So we are looking for help among the science collaborations to find out the work there. So we have a lot of work in front of us, and we're going to be continuing to do this, throughout this year and the coming year. At some point, we'll turn the reins over to somebody else, but I think we're off to a good start, and I hope that, by next year, we actually have some progress on the generations of DDPs to show.
Thank you, Todd. So I propose we leave questions for the discussion later. There is just one quick question on Slack about the slides from the DDP community workshop. Are they saved and available somewhere?
There were too many echoes and I couldn't phase my ears properly.
Yeah, they're asking if the slides from the DDP community workshop are available.
I think we have them somewhere. Our website was down, so yeah, we should make them available. I'll ask, James might know, and he's on vacation, so I can't bug him just yet, but I'll see that we look into that.
Okay, let's thank Todd again. So our next speaker is Dan. I think he's online. Are you online? Can you hear us?
Yes, hello.
Okay, I stopped sharing so you can share your screen.
Sure. All right. Oh, that's not showing up in the full screen there, or?
It's full screen.
There we go, thanks. Okay. So I'm Dan Terreno. I work for Rubin LSST Data Management at Princeton, and I'm going to basically tell you about what we, and by that I mean data management and people working on Rubin commissioning, have been doing with Euclid Q1 with respect to data that is now in DP1. So this is basically three categories. One is catalog matching, which I'll show a few results from, but also quite recently. So in commissioning, we have a couple of, well, not a couple, we have several science units that are looking at basically specific aspects of the system for commissioning. I am co-leading one that is focused on galaxy photometry, along with Melissa Graham, who's doing essentially the PhotoZ half of that equation. And so the PhotoZ part of this science unit has recently made PhotoZ estimates using matched catalogs between the object tables that are available in DP1 and the Euclid catalogs and a whole host of a compilation of spectroscopic redshifts and some high quality PhotoZs from a variety of external surveys. I personally looked at astrometry completeness a bit in photometry, although not so much because, as you know, the Euclid and Rubin filters are quite different, but nonetheless. I don't actually know a lot of people who've like gone in and deeply looked at image inspection at the level of, like, I looked at a few images side by side, but I don't really have anything to say about that. I will say a bit more at the end about how we, data management, can essentially ingest or utilize the Euclid Q1 images and at some point provide them to users, which we are not doing with DP1, but could conceivably do with DP2. Okay, so here's one result from catalog matching. This is using a probabilistic matcher I originally wrote a few years ago, basically to look at how we were doing in recovering sources with the DC2 simulations in preparation for commissioning with real data. So this is a small part of the ECDFS field, basically where we have the highest depth in DP1. And I am showing that reference magnitude is the Euclid Viz magnitude, and measuring the completeness as a function of magnitude, that is, what fraction of the Euclid objects did we detect. And there are a couple bars there that also show whether we've classified them correctly. So we have essentially one measure of for star galaxy separation DP1 called extendedness, which is just a binary 1 or a 0. And if it's extended, we think it's extended. If it's not, it's not. Whereas Euclid has somewhat more sophisticated measures, including probabilistic ones, of whether an object is extended or not. But at any rate, Depending on whether, well, which catalog you're considering your reference, here's basically the same plot, but showing purity instead of completeness. So if you're a Rubin user, if you're looking at all the objects we've classified as stars, basically to 23rd magnitude in I-band rather than Viz, we agree pretty well on the classification. And then after that, you'll see by about 24th magnitude, the number counts of stars are actually dominated by galaxies that we're misclassifying. And if you look back at completeness, that also happens in Euclid just at a fainter magnitude of, between 24 and 25. Those number counts are not actually stars, they're just misclassified galaxies. So I did not actually include these plots in the DP1 paper. I just have a summary of the statistics, and part of the reason I will explain in a bit after I go over the astrometry. So this plot is showing for matched objects, there you go, as a function of the Rubin I-band magnitude, basically what is the delta in the RA. Now, this is our fiducial astrometry measure. We only have one method of model fitting astrometry, whereas Euclid, I think, has several others, and I'm not going to show that. Put him away. Anyway, my broad conclusion from this, you can see that separated between stars and galaxies. The stars have smaller residuals in astrometry, as you expect. My broad conclusion from this is that basically everything looks fine. Partly this is because we're using the same Gaia DR3 reference catalog, and also the epochs were quite similar in, I think they're basically 2 months apart, the Euclid and the ComCam images that were taken last year that are in DP1. And this is the same plot, but declination instead of RA. There looks to be a small offset. If you look at basically the thick red line, that's the median offset. For galaxies, it is slightly different from 0. Could be something to do with uncorrected DCR or something else, but it's not a very large offset, and I wasn't terribly worried about it. So I didn't look into it any further and basically concluded that the astrometry looks fine to first order for both stars and galaxies. I should say, if you compare to other catalogs like the HST catalogs, which I will show a little bit, the epoch differences are quite large, and you actually have to worry about proper motion and then also star galaxy classification for faint objects where you're not even sure if they are stars and have proper motion or not. Now, as I said, the PhotoZ group has this large cross-match catalog, and they've very recently, as in a few days ago, done PhotoZs using both Rubin and Euclid colors, but I don't have any conclusions from that just yet. For other fields like Cosmos, which I see is just barely in the Euclid footprint, that's right, but very close to the ecliptic, so not getting the full deep field treatment like ECDFS. There are catalogs like Cosmos 2025 that have combined imaging from a number of surveys. Cosmos 2025 actually was mainly done to process the JWST images, and I see they used quite similar, basically a quite similar pipeline to Euclid. And they also have a quite helpful SpecZ compilation. So this sort of thing, which is, I'm not sure which one of the DDPs this would fall under, but having a kind of cross-band, cross-instrument optimal detection catalog would be very helpful, because obviously we use the space-based images for deep blending and detecting objects that are very close together where they're available, and the ground for depth and colors. And having this for all the DDFs would be great, which is why I asked if we're going to have, if the ECDFS region is going to get similar treatment to the Euclid Deep Field South, which apparently it's not. But at the very least, there are useful things you can do with just from the public releases. On the other hand, this is a very non-trivial effort. So part of what I did basically a sequential rather than a multi-catalog cross-match, doing first HST to Euclid and then Euclid to LSST, and saying, you know, HST should be the most reliable modulo the differences in epochs. And really what I was looking for was, can we say which detections are most reliable? Obviously, if it's matched across all three instruments, then it should be fairly reliable. But then where are the false positives or false negatives? And can we learn how to tune our detection algorithms based on that? So this is a plot from basically the region of ECDFS that has HST coverage, which is pretty small, but still it has, for most of it, 3 to 4 different filters. So what I did was, in gray, these dots are basically the reliable matches that have a corresponding object in all three HST and Euclid and DP1 catalogs. And I plotted the Euclid positions of them, and then the blue dots are the ones that are detected only in Euclid and don't have a match in either HST or DP1. And you can, well, depending on how large these dots are, if you can't see them on the screen over there, if you just open the PDF on your laptop later, you'll see a lot of them line up and look like they could be satellite streaks or other forms of false positives. Now, I should say Euclid has a column called a spurious probability, and I've cut out the things that have a spurious probability greater than 20%. So clearly some things still remain, even though I've used that column. It's very helpful to have something like that. We haven't provided a similar, a comparable measure in DP1. But really the overarching point is you need to be careful when you do your sample selection here. And I would ideally like to have all members of, well, basically anyone involved in producing the catalogs that go into cross matches to determine what is the best way to do sample selection, not just with their data on its own, but also for purposes like this, where you're combining different data sets. And you can say the same point about star galaxy classification as you would for, you know, some kind of reliability indicator. This is basically the same plot, but showing in red the objects in HST, in the HST catalogs, which incidentally are this fairly recent HLF reprocessing. The images themselves are old, but the reprocessed catalog is more recent. And if you look carefully at some of these, it's not going to pop out on the screen, but a lot of them are basically false positive detections around bright stars. Sometimes diffraction spikes, sometimes you know, kind of in a ring pattern around whatever they define as the aperture for that star. Okay, so the last thing I wanted to talk about was how could we hypothetically provide this data in a way that users, for example, of the RSP would be used to, or to do any kind of joint processing, either for the purposes of you know, quality assurance by us in data management, or for whatever other cases. So basically what we would want is Euclid imaging following our own sky map, and I'll explain a little bit what that is soon. I'm started work on this, and there's a link to where I'll be tracking that if you have DP1 access and are interested in following. The thing is, the images will not have aligned WS solutions, so that they will not be pixel matched, which is something that is very convenient if you want to do, you know, basic aperture photometry or any kind of joint processing without having to account for these differences in the WCS. Because the pixel scales of Euclid and LSST are just a factor of 2 different, it is very much feasible to make coads or mosaics, if you will, that are pixel matched. So how would you do this? Well, I looked up this is one of the Euclid Q1 papers on the MER pipeline, which is basically the co-addition, generation, and processing part of the Euclid pipeline. And it's actually very similar to the sky maps we use for DP1 and are planning to use for future data releases. So we subdivide the sky into tracks that are basically rectangles of constant RA and dec at the top and bottom. Euclid seems to do basically the same. The main difference is the Euclid tiles is what they call them, are half a degree across on each side. Our tracts are a full degree. And then our tracts are subdivided into patches, and those are 10 by 10 per tract. So I didn't go through the effort of drawing the equivalent LSST tract on this, but it would be basically 4 of these tiles. I did notice that, interestingly, Euclid manually adjusts the tiles so that large galaxies are covered in a single tile. So that tile in the very middle of this, ending in 273, has its border shifted down a little bit to cover some large galaxy, which presumably is near that border. We have not done anything like that. The one main difference between the ways we do our sky tiling is the Euclid tiles, they overlap slightly with each other, so they have what they call an extended area and a core area. We do essentially the same thing. The main difference is Euclid defines their inner core area as a function of heel picks. So that's the magenta
Yeah, 1 minute.
polygons. Sorry?
1 minute.
1 minute, okay. And we define our inner areas as just rectangles. So we could essentially make something very similar and probably compatible, just having a rectangle that covers the same area covered by these heel picks, and vice versa for Euclid. So this is basically the main question I want to ask. How much effort would it take to make coads in another sky map for either survey/project? For our side, our coaddition tasks also do detection and background subtraction. So making coads for another sky map is somewhat more non-trivial than you would think. We don't necessarily have to go through the process of making a whole new measurement catalog, and we definitely don't want to distribute something like that. But if we make different coads on a different sky map, they will have different detections on them. So that might be something that's useful for QA, but probably not for something we actually release. Is it easier for Euclid to make coads in the LSST sky maps? I hope so, and the sky map definitions are publicly available, and we can help anyone in Euclid interested in doing that, or at least determining how feasible that is. The last thing is, I see in one of the Euclid papers, they essentially measure plans, they have plans to measure force photometry on rewarped LSST coads that are also interpolated to the Euclid pixel scale, which means splitting 1 pixel into 4, essentially. And I just want to caution against that. This is basically something you should only do as a very last resort, because, as you know, coaddition involves warping and adding together and adding covariance into images that is difficult to quantify. So rewarping and reinterpolating is something that will degrade image quality, and you should only do as a last resort if you can't do anything better. And I will end there.
Thank you, Dan. We have time for one short question.
Hi, Dan. Thank you very much for your analysis. I would like to point out that in the comparison between the Rubin and the Euclid data, the Euclid data are shallower, and all the detection that are for magnitudes much fainter than the detection limit, you will find artifacts that are due to instrumental effects. So that is something that is well known in the Euclid Q1 papers. You can find more references. So if you go back to your figure, I would like to ask if you're using BIS data or NISP data, so infrared or optical.
This is
for the photometry, for the not these figures, 2-3 figures afterwards, when you were showing the photometry, and that you couldn't match Euclid detections with Rubin detection. Yes, that one. So you find some these streaks are not satellites, so there is some instrumental artifacts. And if this is a near infrared image, so are you comparing optical or near infrared images with Rubin?
So the matching is almost entirely astrometric. Basically, we only use the photometry to disambiguate cases where there are multiple matches, so blended objects. And there we
By-
used I-band matched against Euclid Viz.
This, okay.
But that's
So-
basically irrelevant. It only changes the match for less than 1% of sources.
Yeah, because it's NISP, if you go much deeper than the detection limit, you would find artifacts. Is very well known. And in any case, if the image is very shallow, if you try to match something that is much fainter than the detection limit for Euclid, you will find artifacts just because they are artifacts at that faint magnitudes. So you should make a magnitude cut when you are comparing it. So I don't know if you're doing that.
There is one, but I don't remember offhand. And
Yeah.
broadly, this is one of many reasons why I didn't choose to include a figure like this in the DP1 paper, and probably won't in subsequent works for a while until I understand all of those effects.
So this is Todd Lauer. I just want to say your last point. I haven't worked directly with LSST data, but with the size of the LSST pixels and the pervading scene, if the LSST images are indeed well sampled, and I think that is their usual state, you should not worry about reinterpolation or rewarping. You can do that with essentially no degradation with the proper methodologies.
I will defer to someone like Robert to respond to that if he chooses.
He agrees with Todd. Okay, so Robert agrees with Todd. I will invite everyone to continue the discussion on Slack so that we can move forward. And thanks, Dan, again for the talk. So, next speaker is myself, actually. Okay, so I will briefly introduce a science case, which is the one of transients with Rubin and Euclid together. I don't know why it's not moving. I'll do like this. So I don't need to explain this because you already saw it. This is the footprint of Euclid and the region that is also observable with Rubin. The point is that Euclid is not actually a time domain survey, as you know, but there are a few fields that received multiple observation, as already said before. And these fields are the Euclid deep fields. So there is one to the north, which is not of interest for Rubin because it's not observable from south. But this is extremely important because within this field, there is also a self-calibration field, which is receiving mounted observations, and we are doing a lot of work for transients there. And then there are these two fields, the Euclid deep field Fornax, which includes the Chandra deep field south, and even more important, the Euclid deep field south, which is part of the DDP, and you heard about it. So these fields are important because they will receive about 40 visits. And so in synergy with Rubin, you can study transients combining the bands. Yeah, I'm sorry, I'm not sharing slides for people at home. Okay, can people on Zoom see the slides?
Yes.
Okay, I just showed the Euclid footprint, so you missed nothing so far. So these are the Euclid deep field that receive multiple observation. And what I want to mention, so I'm speaking also on behalf of the supernova transient working group of Euclid. We are doing some work on the self-calibration field, which is located to the north and is receiving about monthly visits for 3 square degrees. So about albeit Euclid is not a time domain survey, we developed our own pipeline to do different image analysis. And so we are using these repeated observations to detect transients using this. And this is just an example of one image that you can see. And we are producing many images using templates that are built using this field, and we are detecting a lot of transient. So again, this might be not of interest for Rubin, but we are testing this pipeline, and this can also be applied on the other field, especially the Euclid deep field south. Now, the good thing about this technique that we are testing here is that we are finding a lot of transient. So far, with 3 square degrees and about 1 year of observation, we found 2,000 transient candidates. And you can see the distribution here, magnitude. This is 2.5 sigma magnitude on different images. So we can go extremely deep with this self-calibration field. So the good thing is that we have very high expectation for the deep fields because the area is much larger. But of course, the observing cadence is not tailored for time domain because we will have 40 visits in the 5-year survey time. And also, we don't have this cadence for photometric classification, but here is where Rubin can help. And this is why we care so much about the DDPs. Is the PSF magnitude that you measure on the difference image. This is the signal to noise is 2.5 on the difference image. Sorry? Yeah, well, it's a very low threshold, yeah. Yeah. I don't have the plot with 5 sigma, but we also have many sources with the 5 sigma threshold. I don't have a light cursor to show, but we will show soon with papers that we're going to publish. So this is an example of what we can do with Euclid. This is a paper that was published with the Euclid Q1 data. So we were using known transients reported on TNS, and there is just 1 point from Euclid that was part of the Q1 dataset. And what we could say is that we can have both early detections in the near infrared and very late optical detection that can be extremely useful to characterize the transient properties. And also we can study the host galaxy of these transients. And many of these transients were reported as hostless, but Euclid can go extremely deep and with high resolution in the optical images that can help you to study these sources. So as already mentioned, there is a plan for this DDP, and transients are part of this DDP data set. And the broad impact for transient is that you can have joint transient light curve, both in optical and near infrared, and also high quality photometry and a good characterization of the host galaxies, and especially the photometric redshift, which are very important if you want to do photometric classification. So these are a few of the recommendations. Some are already more or less solved, especially the first one, because there is the Euclid field south that was selected as one of these fields where to focus. And there is still the point about the survey overlap and timing. And we were interacting a lot with the SEOC, and we also presented our science case at the last SEOC meeting. And there is the question about the transients alert. And on the Euclid side, we are very close to release the first transient towards TNS. This is the main deliverable that we have. Here I mentioned TVS because I'm talking about transients. The first one is high quality photometry and photometric redshift for galaxies because you can have a better characterization of the SED. And then also joint transient light curve, because as I said, as you can see in these light curves here, you have the temporal overlap for the fields, and so you can improve the photometric classification. So this is just one example of what you can have if you cross-match the observing strategy from Euclid and Rubin. This is the expectation of the first overlap. Here, different colors are the different Rubin filters, and the blue stars here are the expected Euclid observations. And if you make a zoom here, This is January 2026. Using this old version of the baseline, you can see how you have this overlap between the two observations. And we were discussing with the SOC to maximize the overlap and observe as close as possible with Rubin with the Euclid observations. And we also started a precursor survey with a smaller telescope, the VST. This is very similar in terms of pixel scale and sky location to LSST, but of course it's way smaller. It's just 1 square degree. But we started last October monitoring of 4 square degrees in 3 bands with a weekly cadence in the Euclid Deep Field South. And so what we are doing now, we are currently reducing and analyzing the data, is that this can be a precursor of what the DDPs and the synergy between Euclid and Rubin on the ADFS can be at a smaller scale. So concluding remarks is that, of course, you know that Rubin is great because it's tailored for time domain, but it can still be improved if you add information, especially in the near infrared band. And Euclid can provide this information, but of course it lacks the high cadence to do transits that Rubin can do. So if we merge the two datasets, we can do a lot of things. And I think this is the purpose of this kind of discussion that we are having today. So thank you very much. I think we can also move questions later because we have last talk, and then if there is time, we have discussion. So our last speaker, let me change the slide. Is this? Yeah. Okay. Okay, next speaker is Saro Romanowski. Am I sharing online?
Yes, it's good.
Okay, it's sharing. Okay, yeah. Okay.
All right, thanks for the chance to speak here. I wanted to talk about some projects have going with joint Euclid and Rubin analysis. So some first science results from looking at both beautiful data sets. And the themes of nearby objects, dwarf galaxies, and globular clusters. Oh, it's not working. There it goes. So just a little bit of background on the science of dwarf galaxies. It's a real active area of research in extragalactic astrophysics of understanding the formation of dwarf galaxies using them with probes of dark matter. There's a lot of unsolved problems, which I don't have time to go over, but a lot of interesting science to do, including there of globular clusters. The dwarf galaxies are factories for globular clusters, and we don't understand a lot of the variations that we're seeing observationally in those. Just a little bit of the physics involved. A lot of the uncertainties has to do with feedback processes in dwarf galaxies and how this works and how it affects them. There's active models of what we call a bursty mode of feedback or a breathing mode, where strong feedback causes dwarfs to expand and contract and to form dark matter cores. And some work to test this with observations. And so things like looking at their star formation histories and their structures, morphologies, dark matter content. Globular clusters are interesting objects from early epochs of the universe. There's a lot we don't know about them, but we're starting to see them forming in high redshift observations from James Webb and a little bit with Hubble. But what we still need is a good low redshift baseline of a full inventory of globular clusters in all environments and all galaxy hosts to constrain the models. So this is where the joint ground and space-based data can be really powerful. And various people have worked on this and put out some white papers on how many globular clusters you expect to detect in the nearby universe with Rubin, or with the full 10-year survey. 10 million globular clusters estimated to be detected. And you want to move beyond candidates to pretty high confidence identifications. And here you can combine the broad wavelength coverage from the U-band out to the near infrared if you have telescopes that have both of those jointly, and also high resolution to weed out background galaxies. So this is a nice plot that shows the imaging depth for example SCDs for globular clusters. And what you can kind of see here is that the U-band, a globular cluster, the U-band depth of LSST will be equivalent to the near infrared depth of Euclid. So it's sort of well matched for this particular science goal over here out to the H-band. And this is an example of how you can do color analysis to use from the U-band out to the infrared to discriminate globular clusters from other types of objects, including foreground stars. So this is a early science result. I believe the first joint result between these two telescopes, the first extragalactic result from Rubin of, this is in the ECDFS field of an ultra diffuse galaxy, which is a really interesting type subset of dwarf galaxies where you can hopefully appreciate the greater depth that Rubin provides, and then also the higher spatial resolution that Euclid provides. So you can analyze not only the properties of the galaxy, but the globular clusters are there pretty well resolved, but actually deeper in Rubin than in Euclid. Done some SCD fitting and don't have time to go into the implications of this, but go see my poster if you, or the paper if you want to know more. So what we're working on is a multi-year project to do a survey of dwarf galaxies nearby with primarily with Euclid, but combining other data sets were available. And we're looking at these different properties of dwarf galaxies, a full range of environments, surface brightness, and comparisons to simulations. So the different surveys, of course, are with Rubin, also eventually with Roman and DESI and Sphere X. This is just a kind of an overview of the sample of about 6,000 dwarfs. It doesn't sound like much, but for dwarf galaxies, getting a full range of environments and masses and everything, there's never been a sample quite like this with all the different high quality data that is going to be available. So we're working from what we call a distance and complexity ladder from nearby objects in the local group out to about redshift of 0.1. This is one that's a local group dwarf where we're studying star clusters. We can calibrate them with different methods. A student, Zach Kustier, has a poster out. You can see this. And it's kind of a preview of the data quality. This is what Subaru Hypersuprime Cam. So it's a kind of a preview of the data quality we'll get with Rubin actually already observing this as part of SV. And also with Roman eventually as kind of what you can do by combining the data sets. Another thing just to briefly mention, I'm interested in low surface brightness objects in general. Another area of importance is stellar streams and substructures around galaxies, not just around Milky Way, but lots of galaxies to get statistics compared with cosmological galaxy formation models. Here's an example of one example Milky Way type galaxy where you can see some interesting accretion event happening, and you can see both in Euclid and in Rubin, and they have different complementarities. At Euclid, you tend to see it in greater detail, and in Rubin, you tend to see these structures in greater depth, and of course extend the wavelength baseline for analyzing the stellar populations. This is another student working on this, undergrad, Gina Johnson, and hopefully we'll get a paper on that soon that you can see. Yeah, anyway, thanks. I'll take any questions.
Questions, we can have also questions for the other speakers. So we have 5 minutes left for discussion. We already have one here.
It's not actually a question, it's a forum for future discussion. So my name is Stephen Gwynn. I'm at the Canadian Astronomy Data Center. One of my hats is running the Canadian LSST IDAC. Another one of my hats, though, is getting Euclid data into Canada. And the third of my hats is running the Unions survey, which of course is the LSST at the north that Jean-Charles mentioned. Why am I telling you this? It's because I've been running a series of photometry forums for Euclid where we discuss photometry within the Euclid pipeline, but also from the external surveys like Unions. So far, there hasn't been any presence from LSST. I think it's high time there should be as you start, I mean, as this session has shown. The next one is going to be in Paris, tentatively scheduled for November 20th and 21st of this year. So that's the week before American Thanksgiving, in case you were looking at your calendars. But I think it'd be a good, well, I think it's essential that at least somebody from here shows up for that. It's the Euclid Photometry Forum. Okay, so we're just actually working through the exact dates at this point, but it's tentatively scheduled for November 20th and 21st.
Someone else wants to add something?
Is it, so from this session, could somebody maybe just say something about how many of the derived data products are sort of aspirational at this point, and how many have a realistic plan for being produced? Right? I mean, so
well, we don't have any in your hands right now, so they're all aspirational would be the glib answer. I think though that, you know, we're on a path to get the DDP2 done, and you know, there is an understanding of how to do DDP3, and that will cover an awful lot of ground among the subsidiary DDPs that generated those things in the first place. So, you know, I think we're off to a good start, but you know, as I say, we don't have any in our hands yet. So.
Yeah, I'm kind of a newbie to Euclid stuff, but I was just wondering, is there like a Slack channel or a place where people are discussing Euclid/Rubin synergies? No. Okay, just asking.
Yeah, I remember there was the forum, but I think it's down.
Well, actually, it's off. We haven't been. There's been a bit of a mishap on keeping the IP alive on the forum, but typically the DDP forum is a place where we would want this to take place, and we'll have it up and running soon. I promise.
Thank you for the reply. Any other comments or questions?
I had one, but I think, well, Simona just left. I was going to ask, is there anybody from the Paris and Munich pair of groups that could tell us a little bit more about that demo group's activity? Simona could have done, but she just left. Nope. Okay, we should follow up. I was going to ask her how it was going, whether they were making DDP2 from both the Euclid direction and the Rubin direction, and where they were planning to put the outputs so that everybody can see them. So I'll take an action to ask Simona, and I'll put it in the meeting Slack channel for this session.
Other questions?
If I may answer a question Dan had actually about the Chandra field. Any deep field that is common to Euclid and Rubin will be equal DDP. The only difference between South and Chandra, in your case, is the fact that in one case the pixels are available to everyone, but then the regular sort of quote regular DDP will handle EDF South and EDF Fornax just the same way. So you have them both.
For the clarification? So we are at the time of finishing the session. If there are any very quick, urgent things to ask. Otherwise, thank you very much, both remotely and in person for this discussion. And I hope it was productive to you. Thank you again.